Got an exam coming up and finding yourself a bit stuck on those electromagnetism problems? Well, you are in exactly the right place. We're going to cut right through the confusion, break down the formulas you actually need, and give you a solid step-by-step method for solving these numericals. Let's jump in. I mean, this is the big question, right? It's the whole challenge with electromagnetism. We're dealing with all these forces that are literally invisible. So how on earth do you translate that into a real answer on your exam paper? It really just comes down to having the right tools in your toolkit and a clear plan of attack. And that's the key. The forces might feel abstract, but the math behind them, it's totally real. And honestly, it's pretty straightforward once you know the rules of the game. So that's my promise to you right now. We're going to give you those tools, we'll lay out the essential formulas, and, more importantly, a repeatable method you can use every single time. Let's get to it. Okay, first things first, let's talk about the absolute core formulas you have to know. These are your bread and butter for calculating magnetic force. Our first heavy hitter is F equals QVB. This is how you find the magnetic force, that's F, on a single tiny charge, Q. The key ingredients are the charge itself, how fast it's moving, that's its velocity, V, and the strength of the magnetic field, B. And here's the crucial part. If that charge isn't moving, its velocity is zero, which means the whole force is zero. So remember, no movement, no magnetic force. Simple as that. So what happens when you've got a whole flood of charges moving together, like the current in a wire? That's where our second big formula comes into play. F equals ILB. This gives you the total magnetic force, F, on a wire that's carrying a current, I. For this one, we care about the length of the wire that's actually inside the field, L, and of course the field's strength, B. And this is how they connect. It's actually pretty cool. Think of F equals QVB as the super zoomed in view, the force on just one little electron. Then F equals ILB is the zoomed out big picture view. A current is just tons and tons of charges flowing together, so this formula is really just adding up all those tiny individual forces. It's a perfect way to see how physics scales up from the tiny to the massive. All right, that's enough theory for now. The absolute best way to get comfortable with these formulas is to actually use them. So let's walk through a couple of classic examples and see how it all works in practice. For our first problem, we're going to need Faraday's law of induction. Now, this is a really powerful idea. It basically says you can create a voltage, which we call an EMF, in a coil of wire just by changing the magnetic field around it. This is literally how electric generators work. As you can see from the formula, the induced EMF, that's the epsilon symbol, depends on the number of turns in the coil, N, and, this is the important bit, the rate of change of the magnetic flux. Okay, problem number 1. We've got a coil with 400 turns, the magnetic flux changes by 0.1 webers, and that change happens super fast, in just 0.001 seconds. The question is, what's the induced EMF? So, how do we solve this? We use our simple 3-step method. Step 1, just list out everything the problem gives you. It really helps keep things organized. We have N is 400, the change in flux is 0.1, and the change in time is 0.001. Step 2, pick your tool. The problem is asking about induced EMF from a changing flux, so that's a dead giveaway. We need Faraday's law. And step 3, you just plug in the numbers and solve. You run that calculation, and you get your answer, 4 volts. See? By following that simple process, you take a problem that looks kind of complicated, and you break it down into a simple calculation. Okay, now for a slightly different situation. What if, instead of the magnetic field changing, we move a wire through a constant field? Well, that also creates a voltage, and we call it motional EMF. The formula here is epsilon equals BLV, where B is the field strength, L is the length of the conductor, and V is how fast it's moving. And here's problem number 2. This time, we know the speed is 10 meters per second, the magnetic field is 0.8 Tesla, and the induced EMF is 8 volts. But the question is asking for something different. What's the length of the conductor? We're going to follow the exact same method. Step 1, list our givens. V is 10, B is 0.8, and epsilon is 8. Now, step 2 is where you got to pay attention. We know the formula is epsilon equals BLV, but we're solving for length, for L. This is a super common thing on exams. You have to rearrange the formula. A little bit of simple algebra gets us L equals epsilon divided by B times V. Step 3, substitute and solve.
And the math works out nice and clean. The conductor is exactly 1 meter long. See? Same reliable method, just with a little algebraic twist.
All right, we've gone through the formulas, we've used the method. Now it is your turn to put what you've learned into practice. Here is your challenge problem. You've got an 8-Newton force on a conductor that is 20 centimeters long. The current flowing through it is 40 amps. Your job is to find the magnetic field strength, B. Now, here's a little pro tip for you. Always watch your units. That 20 centimeters, it's going to need to be in meters before you solve. You have everything you need. Think back to our force formulas at the beginning. Which one connects force, current, and length? Go ahead and pause this explainer right here, rearrange that formula, and solve for B. Give it a shot. And the answer is 1 Tesla. How'd you do? If you got it, fantastic work. If not, no worries. Here's the quick breakdown. We need F equals ILB. We rearrange it to get B equals F divided by I times L. Don't forget to convert 20 centimeters to 0.2 meters. Then it's just 8 divided by the product of 40 and 0.2, which gives you exactly 1. And there you have it. We started out talking about these weird, invisible forces, and now you have a clear, repeatable method to calculate them. It's a great reminder that even the most complex-sounding ideas in science can usually be understood with the right formula and a clear process. Keep practicing these, and you are going to absolutely master the stuff.